All right, let's get into some more electricity. We'll review a charge is measured in coulombs, represented by a capital C. The charge for one electron is 1.6 times 10 to the negative 19 coulombs. Because it's an electron, it would then be a negative 1.6 times 10 to the negative 19. If we're asked how many electrons are in a coulomb, well, we know one electron has this much charge, right? So we can just do a little bit of dimensional analysis. And there we have it. Coulombs cancel out. We are in coulombs. We want it on the bottom, so we get rid of it, and we want it in electrons, so we put electrons on top. One electron is going to be a greater number than just the elementary charge. Bad word. The elementary charge will be given to you on your exams. This is what it's going to look like, and this is where you can find it. This is in your constants page. Current. The rate at which charges move through a conductor. You can think about current as the water in a river that's flowing. The water is the flow. Current is the flow of the charges. Current flows, water flows, because there's a difference in elevation, right? Current flows because there's a difference in potential we're going to get into. Flow of electrons. Symbol is I. The unit is an ampere. What in the world is an ampere? 1 ampere of current is the amount of current in each of the two infinitely straight wires 1 meter apart, experiencing a magnetic force per unit length of 2 times 10 to the negative 7 newtons per meter. More on that later when we deal with magnetism. All right. Amperes, unit for charge. Coulomb, unit for current, is A. So A is a coulomb per second. Coulomb per second. This equation, if we use the symbols instead, would be I equals Q over T, where ampere is the unit for current. Current is represented with the letter I. C is the unit for charge, represented with Q. And then seconds are the units for time, represented with, of course, T. Let's try this. How many electrons flow past a given point in a wire every second when the current is 3 amps? Go ahead and hit pause. Try that question. And there we go. I don't know if I gave you enough time, but it was basically the same exact question that we just did, but there's a 3 in front, and we're dealing with time now. So we're using I equals Q over T. Why do the electrons flow instead of protons, neutrons? So the electrons flow because the electrons live in the outside of the atom, or just outside of the atom. If we were looking at protons flowing, we would first have to break apart those protons because they're bonded with a strong nuclear force to neutrons and other protons. So you would have to break apart that. That's a lot of energy. So electrons, meanwhile, can jump from empty valence shell to empty valence shell to empty valence shell down a conductor. So they're easily transmitted. As electrons flow in a current, they have a net velocity down the conductor. So as they're jumping down these valence shells, they have a speed, drift speed. Electron drift. In a time, delta t, there's a certain volume of electrons flowing through a wire. So area, this is the cross-sectional area.
Recording.
So we can get volume using area pretty readily, right? So we have a cross-sectional area times the speed that the electrons are going, v, times the time that it takes for those electrons to travel that certain area. Volume from that. If we know the number of electrons per unit volume, then we can just find the charge. So N is the number of electrons. And if we know the number of electrons, we can add that in there to get NAVTQ, right? There we go. So all together, time on top, time on bottom, we get I equals NAVQ. I is the current, N is number of electrons per cubic meter, V is the drift speed in meters per second, Q is the elementary charge, A is cross-sectional area of a circle, pi r squared. Here's a problem. Try this. Pause the video, work it out, and then I'll be back to give you the answer. We know the current is 1.5 meters given to us. Number of electrons per cubic meter given to us. Q, elementary charge. So Q is not given to us. It's kind of like acceleration due to gravity, or the gravitational field. G equals 9.8 meters per second squared. It's not specifically given to you, but it's always there. It's always there. Okay. Cross-sectional area here. Because we were just given the diameter of the copper, remember radius is half of your diameter. Plugging that in, we get, boom, 0.038 meters per second. All right, here's another one with electron drift. Try this. Multiple choice. Which of the following is true of the current and drift velocity at x? Pause the video. Think about it. Work it out if needed. All right, here we go. Current is not going to change. So V equals I over NAQ. If we're looking at half of the radius, then the area is going to be a quarter, because area is pi r squared.